Hi everyone, this is Kerim Baran with SolarAcademy. I am here today with Blair Reynolds of Dynapower, and Blair has a great story in solar, and he has been in every corner of solar that the common people would know about in our industry. Today we're going to talk about some really important issues that concern the grid and the stability of the grid. But before we get into that, we'll talk a little bit about Blair's background, Dynapower as a company, and then we're going to dive into the major problem of frequency regulation or inertia, rotating mass, and some important topics like that. So, Blair, welcome. Thanks for making the time.
Yeah, thanks for having me, Kerim.
Right. So let's start with your background. Tell us as far back as you want to go, high school, college, after. So like how did you end up in solar? I see on LinkedIn you have a physics undergrad degree,
Sure.
and I see that you worked in one of the oldest San Diego installers. I'm based in San Diego, Sullivan Solar Power.
Yeah.
Like what drove all those jumps? And you are in North Carolina right now.
Yeah, that's
Um,
right.
so are you a born and raised North Carolina person, ended up in San Diego? Tell us, yeah.
Yeah, born and raised in North Carolina, or at least that's what I tell people. I grew up in Asheville, North Carolina, up in the mountains, and
Nice.
yeah, a lovely place to live. It's very different now than when I grew up there. Of course, it's been very much discovered by tourism. I went to undergraduate college down in Charlotte
Yeah.
area, a little school called Davidson. I
Yeah.
was recruited there to go play football and had a great career there. Just before the Steph Curry era,
Yeah.
if you're keeping track of sports, he really helped put the school on the map. But yeah, tiny school.
Yeah.
And I chose the least popular major there. Like literally, I was a physics major, and at a school of 1,600 students. And so my senior year in our graduating class, there were three of us with in the physics program. So
Wow.
yeah, in fact, there was a time in my senior year where there was just one other student and I enrolled in a semester long course, right? So a lot of personal attention, I would say. But yeah, doing that program and being a full time athlete, which is essentially a full time job
Yeah.
plus some, I would say, was quite an experience. And yeah, definitely put me on a path which sort of led me into the career that I'm in now, which of course renewable energy and large scale battery storage. You mentioned San Diego. Yeah, it's a very special
Yeah.
place to me as well. That's not only where I met my wife. I lived out there for at least up and down the West Coast, but primarily in San Diego for about 6 or 7 years. And that's where I found the solar industry. And this
Yeah.
was in the mid
2000.
2000s, 2007, I think is when I first got my first job. But I actually attended a Solar Power International up in 2006. So that was up in San Jose, and I've been attending every
Wow.
one ever since. But yeah, that was right, around this transition that was happening, particularly in places like Southern California, where we were seeing an uptake in more energy efficiency and renewable generation and home solar, right? I mean, that was SDG&E was doing quite a bit at the time to incentivize homeowners to go solar, including with the California Solar Incentive Program (CSI). And yeah, so it was a really great time to get into the industry. My first job was selling to homeowners over a kitchen table, probably like
Yeah.
many of us.
Yeah.
But I quickly learned other aspects of the business, including the sort of technical side, including the design of systems and how to actually get permits through approval, learning the National Electric Code, learning sort of the practical electrical side of the business that you don't learn at college or university.
Yeah.
And was yeah, I knew
And
right
then,
away I found my career. That was
yeah.
that was obvious.
Wow.
Yeah.
That's cool. And that took you to a graduate degree in Australia, studying.
Yeah, yeah. I was working in the industry for a couple of years. In fact, at the time, I got picked up by Sharp Electronics, who was, you might remember,
Yeah.
one of the original
Early.
manufacturers of solar modules in the U.S.
Yeah.
I was working for them as an applications engineer, and had an opportunity to put that on hold and go back to school and pursue a master's degree specifically in photovoltaic engineering. And that was with a program in Australia, University of New South Wales, made very famous by Professor Martin Green, who was sort of the pioneer of high efficiency silicon solar cell design. In fact, I really think can be credited for the PERC technology that we have so much, gigawatts deployed around the world. He had in fact set the world record. His lab did back in 1995 for single junction crystalline silicon efficiency at 25% on a single cell in 1995. And in fact, it wasn't until I think 2012, 2013 when that record was actually beaten. And it was beaten by SunPower, believe it or not. So I did a master's program down under, had a wonderful time, was working throughout that experience, learned the Australian codes and standards. And yeah, if you haven't been there, you should go. It's far away, I get it, but it is absolutely a wonderful place. And I was just, exposed to, gosh, at the time, large deployments of residential solar. I mean, it was every third house in the cities there, the metropolitan areas had a small, 1.5 kilowatt PV array on the roof, and that was primarily driven by the not only the economics but also a rebate program that had a cap on it. So like eight modules on every roof. It was great, and so it was a fun time. I went back to work for Sharp after I graduated that program, and was sort of kind of right there until the very end when they decided to pull out of the U.S. market, and did a little stint over at a German company called SolarWorld, also very well known for U.S. manufacturing of solar.
We sold quite a bit of SolarWorld panels back in the day at my old company, Civic Solar.
Yeah, and isn't it so funny to see that whole trend come back around full cycle? Yeah, full circle, and yeah. So, but really, what I was doing was, just it was DC, right? The DC side, which eventually led me to batteries. I mean, there's not a lot different in terms of the basic principles of current, amps, voltage, short circuits, fusing designs, all this kind of stuff on a PV system versus an energy storage system, battery side. So I got into that business around 2013, 2014 with a company that was trying to compete with basically the Tesla Powerwall, making a residential home battery system. And this was really before the lithium stuff really took off in a big way. So I kind of got in on the forefront of that and learned a lot of the technical aspects and practical aspects too. Like, what does it actually take to get a battery system designed, installed, permitted, and approved by the utility? It was a cool time. I transitioned over to Enphase, believe it or not. I was there, and I helped them launch their AC battery. It's gone on to be a very successful product line. The Gen 1 battery, I'm not sure if you remember, it was a grid following product only, right? So it was not doing backup power. It was really a time-based charging and discharging schedule that worked really well in markets that had basically been built up around feed-in tariff models, where you basically get paid for all your generation, and over time those feed-in tariff markets, the value for that generation started to get ratcheted down significantly. And so in those markets, there was definitely an incentivization to install a home battery system and basically store your excess solar, and then use it yourself in the evening time. And so that battery was really the right technical solution for those markets, which coincidentally Australia was one of our biggest markets.
Wow, I don't know.
Yeah. I've since been working in the inverter side of the business after doing the batteries and the stint at Enphase, and that's really where I got exposed to Dynapower. In my current position, I was actually a customer of Dynapower's for several years with a global solar and energy storage inverter manufacturer called SMA. I started off on the residential side of their product management division, and then moved over to the utility scale, large scale storage side of the business. And there at SMA, I was the global product manager for their DC coupled product strategy, as well as the global manager for the grid forming technologies, which sort of leads us into the discussion here. But it was in that role that I found Dynapower. I was interfacing with them almost on a weekly basis. We were white labeling one of the products that's been very successful for Dynapower, the DC to DC converter product, and really got to know the folks there well, and was fortunate to have an opportunity to come and join them and lead their renewable sales division. So in my current title, I'm the director of the renewable division for Dynapower, primarily responsible for front of the meter solutions like large scale DC to DC converters and energy storage inverters. Yeah, that's a little bit about me.
Yeah. Thank you for that background.
Sure.
You definitely have wealth of experience that I would love to do many more conversations with you, diving into different forks of that path.
Yeah, thanks, Kerim.
Yeah, hopefully in the future. Let's talk a little bit about Dynapower. So you're responsible for the renewables and e-mobility, I guess, business unit.
Yeah, that's right.
And revenue driving revenue for that. Can you give us a little bit of a big picture view of Dynapower and where that division sits? Kind of like, because from what I understand, it's a very established large player in the energy power sector.
Definitely a large competitor in this space, but the company came from a really small, kind of grassroots type of organization. Dynapower, 60-year-old company. Yeah. Last year we celebrated the 60th anniversary of the company, and the early years of the business, we were really making small volume custom power conversion electronics, primarily rectifiers and for CNI and mining applications. We've expanded that into more of military and some of these other areas. But it was like me in 2017. Dynapower as a company got into renewables, and it was through our very first bi-directional energy storage converter, and that was 2017. We're now in 2024. We're on our 5th generation of the central energy storage inverter product line called CPS. And our smallest is a 1.25 megawatt variant, and then I have a 2.5 megawatt variant. But yeah, it's been a great product for us. That in conjunction with our DC coupled solutions, so DC to DC converters, we have some really innovative approaches to coupling solar and storage together on a DC bus, and that's really, I think, what put Dynapower on the map. And helped us, grow into a recognizable competitor in this space. And 2 years ago, the company went through another major transition when we were acquired by a publicly traded global company called Sensata Technologies. And Sensata's got us beat. They have over 100 years in the business and like 21,000 employees, locations in 13 countries around the world, and they do around $4 billion in revenue just in 2022. So it definitely gave us an injection that we needed to help us scale at a critical time.
What's the synergies between Sensata and Dynapower? Like, what are their traditional products versus?
Yeah, Sensata makes sensors, but they make sensors that go into a lot of automotive and aviation applications. Yeah. And so I think the typical electric vehicle on the road has something like 20 Sensata parts in it. All of this like LiDAR and radar stuff that we see out there for the self-driving vehicles, all kinds of various electronics and sensors. These are high volume, low cost sort of devices. And through the relationships with the EV industry, Sensata saw a real opportunity to grow their clean energy division. They acquired a smaller inverter company that's primarily used in RV applications, mobile applications, a few years before us, and then they acquired us 2 years back and really helped bring us up to a more mature level and give us a capital injection that we really needed to continue growing and scaling. So yeah, it's been great to have them supporting us, and they've really gotten on board with what we're doing and our culture. And yeah, it's a
Right.
little bit unique. I like it.
Yeah, nice. So let's dive into a little bit of your world then.
Sure.
Tell us a little bit about the product solutions you're responsible for, and then let's talk a little bit about the main problem you're solving in the market these days.
Yeah, I mean it's primarily inverters, and we don't make a solar inverter per se. We make a bi-directional inverter, so that's what you would use in a energy storage applications primarily. It also is used in hydrogen electrolysis as a rectifier. So we're converting the AC to DC and powering electrolysis with it. We have a skid where a 5 megawatt skid that we make with two of our inverters on it, along with a medium voltage step up transformer. And then, yeah, the DC to DC converter products that have been really successful for us. We have a 500 and a 1 megawatt version of a DC to DC converter that allows us to directly couple batteries and solar behind a single inverter. And in doing so, there's quite a number of advantages, but it basically comes down to lower cost, higher yield, and easier permitting, faster interconnection applications, and so on and so forth. Because you're generally applying for a smaller interconnection because it's a single inverter rather than AC coupled strategy where you have two inverters, both sort of competing for that interconnection space.
And this is usually coupled with a utility scale solar farm or similar power
Yeah,
generation source.
yeah. But with the IRA, we're seeing a whole lot more sort of standalone storage going in.
Yeah.
But yeah, as far as DC coupling, what that really means is it's literally connecting solar and batteries. That's really the primary use case. Yeah.
And one of the major problems you solve is the frequency problem on the grid. So let's talk a little bit about that.
Yeah, sure.
What is the frequency problem? What creates that, and how do you manage that?
Yeah, Kerim, I think we can both agree that the world is a lot better off with more clean energy sources than not. More clean energy, less pollution. And so there are some fundamental issues that we have when we try to deploy renewable generation at large scale, particularly when there's already a high population of renewable generators in a certain section of the utility grid. Thinking about it that way. The best example I could give you in recent years is Hawaii. They've really struggled with growing the amount of renewable penetration on their grids while still not creating a debalance or a destabilization of the network.
What's
there.
Hawaii at? I remember it being at 35-40% penetration a few years ago. It's probably gone past 50 plus now, is what I'm assuming. And that was also creating such other dynamics where all the wealthier folks who could afford it were going almost off grid because they could, because electricity is so expensive there, 50 plus cents. Sure. Like it made, like you got a 3-year payback putting your own solar, own battery, cutting yourself off the grid. And that created less customers for the grid, but fixed costs. And it was a crazy story. That first time I heard it was probably 5-6 years ago. Can you give us an update of like how things have evolved since then? And
well, yeah, what you're describing a little bit is the as grid defection, where people basically say, I'm done with being connected to the utility grid. I'm going to be my own power station. And they connect solar and batteries and maybe other generation sources like microhydro or wind, and basically operate their own self-contained microgrid. And it's actually that kind of segues into some of the technology that we'll be talking about here. Is that grid forming technology? Because when you're not connected to a power line, you are your own source of the AC waveform. It's so grid. That's really the kind of the fundamental roots and background for this grid forming technology that we're talking about. Is it comes from the off grid space, because you're generating the sine wave. You're not like latching onto it and syncing with it as grid following inverters typically would do. You really are the source of that waveform, and that's really that grid forming technology that has now evolved to a place where it's creating stabilization. It's leaving the electric grid in a better condition than it found it. That's how I like just to think about it, and is solving some of the fundamental problems we have with deploying large volumes of renewables on the grid. So yeah, the example you used earlier, I remember when I first got into the industry 17 so years ago. Yeah, I heard these sort of theoretical limits about how much renewable penetration we could realistically achieve, and it was on the order of 25%, and then I think it kind of crept up to 30%, maybe 35 over time. But it's always been a talking point in our industry, is that renewables are intermittent. They don't behave like 20th century generators and fossil fuel generators, and they create some stability problems. It's definitely been a political talking point. And yeah, that's really what I'm here today to talk about, is sort of debunk some of those myths, create a little bit more awareness and education on that in that area. Yeah.
So let's do that, because I do believe that in 20 years grid will be powered. I don't think the grid is going away. I don't think we want the grid to go away necessarily. But I think as solar will be the main source of powering the grid, with probably 100, if not more, times nodes of power production than we have today. And most of that will be solar stored into local storage or regional storage. So what are the issues along the way? So, and how do we solve them?
Yeah, I mean, you hit on one earlier, Kerim. You were talking about frequency, and there's just to kind of like level set. There is a fundamental relationship between frequency and load, and of course, when I'm talking about frequency, I'm talking about the 60 hertz, so 60 cycles per second in U.S. electric grids, 50 hertz in most of world markets. But it's that it's that frequency of the AC waveform that we're talking about on the electric grid that we build all of our systems around. And our electric grids have a very tight tolerance, actually, for the level of fluctuations in frequency that we can tolerate. And this all sort of comes back to how our electric grid was constructed, sort of built around 20th century technologies. But the fundamental relationship between frequency and load is an important one to kind of understand. So a sudden increase in load will decrease the overall frequency of the system, just like a sudden decrease in load would increase the frequency of the system. And so conversely, a sudden decrease in generation will cause the frequency to decrease substantially as well, and drastically, in fact. And that really kind of is the fundamental principle that we're trying to solve, or the problem we're trying to solve, is preventing that rapid collapse of frequency when there is an issue, a major issue on the grid. We lose a generator, and we prevent that crash.
Is that the scenario that can crash the whole grid?
Absolutely. Absolutely.
Yeah. And what happens if so I mean, even like, just think of a very concentrated, huge solar farm, big cloud comes over it, that could even crash the grid then on a...
No, because that's not really messing too much with the it's not messing enough with the level of frequency drop that we would be concerned about.
It wouldn't be happening fast enough. Like you would have a failure.
No, we're really we're talking about millisecond speeds here. It's incredibly fast. And so, but you're right in a sense that grid connected inverters have had to sort of evolve over time. We used to, anytime there was a weird blip on the grid, the inverters used to have to drop to cut off, and then they would wait 5 minutes before they would come back online and check in. Is everything stable now? That was a requirement under the UL standard 1741. And we realized that wasn't that worked for a period of time, but it wasn't sustainable to allow us to continue to grow more and more deployments of solar and other types of inverter-based resources on our grids. So we started introducing smart inverter capabilities, things like voltage ride through, frequency ride through, these kinds of things, volt var, where we can sort of inject either active or reactive power into the grid as the conditions would warrant. And that definitely helped create a less instability, for sure, but definitely didn't go far enough to solve the frequency problem, which is really caused by a massive loss of generator failure. And fortunately, these are fairly uncommon, but when they do occur, they can really be a serious problem. There was a recent event in Australia where an entire natural gas generator, it blew, I mean, literally blew up. There was shrapnel, hundreds and hundreds of yards away. And in fact, even but it doesn't necessarily have to be that big of an event. There's a really interesting report that was published by NERC about well, they call it the Odessa disturbance. I'm sure there was been more than one disturbance in Odessa over the years, but this is we're talking about Texas, and this is a particular fault that occurred on a power line there that ended up creating a cascading result that took more than a gigawatt of solar offline, and that's not how we are supposed to be behaving fundamentally. And so NERC did a really good job doing a deep dive into this. How did this happen? And quite honestly, it sort of comes back to the people that are configuring these systems. Are they actually configured properly to create that level of stability and ride through? Are the operators of these plants are they knowledgeable in how to operate them in a way that prevent them from going offline like that after a fairly minor grid disturbance, grid event? And so, yeah, that's really kind of leads us into this topic of inertia and sort of how inertia creates stability and strength for the electric grid. Fundamentally, inertia, it's Newtonian physics, and an object in motion wants to stay in motion, right? And so it's incredibly important that we have a certain level of inertia on our electric grids to create this sort of stability that prevents us from experiencing a rapid collapse of frequency. And maybe I'll use an analogy here. It's you're imagine going along on a train, and you're riding along on a train, and it's all of a sudden you come to an immediate stop. I mean, I'm having a hard time kind of thinking about how that would happen. I guess if there was another train with the same velocity and mass, and they both crashed head on, you'd have a pretty bad day, I would think, if you were riding on that train. So, but that's of course not really what happens. When you slam on the brakes on a train, there's a sort of slow screech that occurs probably over miles of distance. But that's what we're talking about here is really creating that slowing down when there is a problem on the grid. And the longer you can sort of create, maintain that deceleration, the better it is, because it allows other systems to come online and correct that problem with backup systems. But if the trains were to suddenly stop altogether, that would be very, very big problem. That would be hard to recover from. And so
that would be a massive shutdown of the grid. And then to bring that back up, you would have to do it in like subsectors slowly.
Dark starting little nodes of the grid, and it would be a massive problem, not too dissimilar from what we saw in a winter storm in Texas a few years back too, right? So we need to be able to prevent those things from happening. And so the fundamental problem is that inverters typically don't behave like a conventional fossil fuel generator, which is actually using,
they don't have the rotating
motion. Exactly. There is a rotating mechanism, a physical mass. There is this literal inertia happening when that turbine is rotating. And of course, what it's doing is it's connected to a generator. The generator is creating an AC waveform because it has an electromagnet that's being rotated through a series of wires, and that's creating our AC grid. And so when there is a big disturbance or something that could potentially create a drastic drop in frequency, believe it or not, it is that sort of gradual slowing, that decelerization, we call it dampening, that actually creates enough stability to prevent a drastic, sort of instantaneous drop in frequency. The technical term in our industry is ROCOF, rate of change of frequency. We really want to try to prevent a sudden drop in frequency. We really want to try to get that slope more gradual, as the frequency declines, so that we allow more time for other backup systems to kick in. That's really the critical thing.
Novice question here, just because I'm a little bit of a numbers guy. So that frequency of 60 hertz or 50 in the US or vice versa, US, Europe, where does that go down to like 49, 48, 45, or are we talking like 49.9, 49.8 kind of,
yeah,
or even less?
We're in serious trouble if we even lose 1 hertz.
Okay.
So if we go from a 60 to a 59, we're in pretty big trouble. We need to be activating recovery systems right away. And so, yeah, it is a very tight tolerance that we have around the frequency, because it's fundamentally, it's the balance between generation and load. And if you have too much of one or the other, the grid can collapse very quickly.
So what's the Dynapower solution to this situation, to this scenario?
We pretend to be like a conventional generator. We behave like a conventional 20th century generator
with a software and battery coupled solution.
Yeah, exactly. So we take our bi-directional energy storage inverter, we overlay a very tight software control on top of it, which is actually a grid forming software control. It is synchronous grid forming. And that's a fairly new term, so I'll explain it a little more. Rather than being grid forming in a pure off-grid scenario, like the microgrids that we were talking about, in a synchronous grid forming scenario, we're actually constantly operating the inverter in what's called a voltage source mode. So we are actually contributing and driving that AC waveform, rather than being a grid following inverter, which is just seeing a waveform and latching onto it and injecting current. That's a current source mode from a grid following inverter. In a grid forming inverter, we're in a voltage source mode, and we are helping to build upon that waveform. And in a virtual, what we call virtual inertia, is basically it's a software control where we're emulating the physics, the Newtonian physics of that rotating mass. Because with an inverter, it's basically, we're digital. The old generators are analog. We have a lot more ways that we can operate in a digital world. We can adjust that waveform between active and reactive power quite significantly. And in doing so, we can create the same exact behavior that a spinning generator would, conventional, fossil fuel generator. And so it's a really important technology to help create enough level of inertia on the power grid to prevent catastrophic collapse from that can be substantially exacerbated by large scale deployment of grid following type inverters, which is mostly what we have out there these days. So we do it with an inverter with software controls, and then we need a battery, of course, connected to the inverter as a DC source. So it's always a captive sort of reserve of capacity to create that stability. But that's how I like to describe it. What the grid forming, fundamentally the physics that we're creating. The problem it's really solving at the simplest level. It's basically just acting like a giant shock absorber. So when there is a disturbance on the grid, we can absorb that with our basically how we're building upon the waveform. So that it doesn't prevent this catastrophic and rapid collapse due to a very sudden drop in rate of change of frequency. And what these systems are really trying to do is buy time. That's really what because there are plenty of other backup types of systems, including fast frequency response, that our inverters are capable of delivering as well, as well as plenty of other inverters, because there's sort of market mechanisms that incentivize that type of control and behavior. But fast frequency response, key point, is not instantaneous. It takes time to do fast frequency response, though be it less than a second, but still in the amount of time that we're talking about, the time scale that we're talking about to prevent a catastrophic collapse, that's ages. So what we have to do, because fast frequency response is basically, it requires the inverter to measure the signal, process it. There's computing happening, and then it needs to decide, how am I going to react to this signal, this measurement that I just took? Believe it or not, that cycle to calculate and react, is wasting precious milliseconds that we can't afford to waste when there is a drastic collapse. And so what's so cool about the synchronous grid forming and the virtual synchronous inertia is that we are doing that control without any processing time wasted. It's inherent into how we're operating the inverter. It literally behaves exactly like a rotating mass would. There is a slowdown, sure, but with a dampening factor, we can behave like this sort of slower and slower decelerization, buying us enough time by continuing to inject inertia into the grid, buying us enough time for these backup power systems to kick on and then take over and bring the frequency back up to a reasonable level. And so fundamentally, that's what we're doing with inertia. It's also, we're able to inject strength into the electric grid as well. And that's grid strength. It's sort of a not a well-defined term, but there is a measurement that we use for it called SCR, or short circuit ratio. Mm-hmm. And the short circuit ratio is basically it's a measurement of the relationship between the short circuit apparent power when there is a line, like a triple line fault on that particular node in the electric grid. I don't want to get too technical here, but basically the way that we measure the strength of the electric grid is if you have an SCR, a short circuit ratio of 3 or higher, that's a strong grid. Between 2 and 3 is really defined as a weak grid, and less than 2 is a very weak grid. And so why this is an issue is that in a very weak grid, you couldn't even connect a solar inverter or an energy storage inverter. It oftentimes won't even latch. Even the grid following inverter wouldn't even be able to connect and inject active reactive power onto that grid because it is so weak. It's so unstable. I mean, I will plug Dynapower's inverters and say that Dynapower's inverters are capable of connecting and operating on grids that are less than 2 short circuit ratio, wow. Which is puts us into the very weak range. But it's tricky, and so yeah, what do we do? With synchronous grid forming technology, we can actually, because we're building upon that waveform, we can literally inject strength into the grid at that interconnection point and bolster it, which therefore allows us to connect more and more solar and batteries, other inverter-based resources to that grid. And probably the best example I can give you was a project that I was involved with a few years back. It was probably one of the first, if not the first, synchronous grid forming energy storage system that was connected to in the US anyways, to help solve that exact problem. It wasn't envisioned that the project was going to be operated this way from the onset, but what ended up happening was during the interconnection planning studies, the modeling of the energy storage system, it was discovered that this particular part of the electric grid, which by the way was at the very, very end of the Cape Cod, Massachusetts, at the very, very tip of the peninsula there, and because it was so far away, just physical distance of electric lines to the nearest power generating station, that ended up resulting in a very weak grid. Yeah, and with all the voltage losses and everything that experienced along the way. So when this developer came in and wanted to put a large scale battery system there at this location, they discovered that the short circuit ratio was actually less than 1. Wow. And that was fundamentally not possible. We couldn't even operate the inverter at such a low SCR. And so what do? We didn't walk away from the project, said, sorry, tough luck. We actually accelerated development of this technology and got this system interconnected and up and running with by operating in a synchronous grid forming mode, so that we actually left the grid in a better condition with more strength than we found it. Yeah, and that was a really cool story. I mean, I think it really addressed this technical problem in a way that really shows the capabilities of this technology in a way that it's going to be increasingly necessary for us to continue deploying gigawatt scale solar and storage across the world. Storage is growing so fast these days, so I'm assuming most of these
deployments are requiring a grid forming solution like this coupled with it, or can you do it without, or what are you guys seeing? I mean, you guys must have a really strong position in the market and enjoying rapid growth from what I hear.
So it is, everyone I think recognizes this is the future. We have limited reserves of fossil fuel on this earth. We need more clean energy, and we have fundamental problems with connecting inverter-based resources to an electric grid that was built on 20th century technology. So what do? You can either rebuild the electric grid and upgrade it from an analog to a digital type of grid, to use my example, but or you can just simply operate and behave like a 20th century generator, essentially the same outcome. So that's how we approached it. That's what we do. But you're right. I mean, this is a critical technology. People are aware of it, but it's one of these funny things where the technology is ahead of the codes and standards. And so we all know that this is coming. We know it's critically important. But most of the projects that are happening around the world right now with synchronous grid forming are either accidental, like the one that example I told you about, or they're pilot scale, to really try to understand, again, the benefits of this technology, how it can replace other 20th century grid stability devices like StatCons, for example, but also to really understand what's the value of this technology when connected to the electric grid. Like, basically, how can we build market that incentivizes people to deploy synchronous grid forming inverters rather than just continuing to push out projects with grid following inverters? Like, can we create a way to incentivize it through a market-based model? Yeah. So people are studying this. Meanwhile, codes and standards are continuing to evolve and develop, because technically, 1741, the UL standard for inverters doesn't contemplate this kind of operating behavior. So there's a little bit of contradiction there in the codes and standards. Like, if you want to comply with all the UL stuff, you're in a gray area when you're doing synchronous grid forming. And so, there's plenty of great committees also working on developing the codes and standards, sort of rewriting the rules so that allows these kinds of inverter-based technologies to operate in a way that adds strength, resiliency, bolsters the grid, allows us to create market mechanisms around this technology, and ultimately deploy more solar and wind.
Right. Blair, thank you so much for this deep wealth of information you shared with us on Dynapower's grid forming technology solutions. This was
it's a real pleasure. Thank you.
Yeah, thank you for being with us.
Thanks for having me. I'll be back anytime. Let me know. Thank you.